Hello, my name is Tom Wong, and I'll be talking about quantum walk search on Kronecker Graphs. This is work done with Adam Gloss, Joshua Lockhart, Simone Severini, and Konstantin Winscher, and this work is published in these two papers in Physical Review A. So let me start by talking about what a Kronecker graph is. So you start with some initiator graph or some initial graph of m vertices. So this variable m is going to come up throughout this work. So m is the number of vertices in the graph you start with. For example, here is a complete graph of 4 vertices. So you have 4 vertices, they're all connected to each other, and you can describe this how the vertices are connected to each other using this A matrix, the adjacency matrix. So this adjacency matrix has a 0 if two vertices are not adjacent, and they have a 1 if they are adjacent. So if you look here, vertex 1 is not adjacent to itself. There's no self loop or anything, so it has a 0. It is adjacent to 2, so it has a 1. It's also adjacent to 3, so it has a 1, and it's also adjacent to 4, so it also has a 1. And you can go through each row to look at how each vertex, again, neighbors the other vertices. To get a Kronecker graph, all you do is you take this adjacency matrix and you take Kronecker powers of it, or Kronecker products of it with itself. So for example, the second order Kronecker graph of this is K4 Kronecker K4, or its adjacency matrix of this with Kronecker product with itself. So what the Kronecker product is you start with A. So you see how there's 0, 1, 1, 1, and so forth. And when you take the Kronecker product of it with A, you multiply every entry by A. So this becomes 0 times A, which is 0. This becomes 1 times A, which is A. 1 times A is A. 1 times A is A, and so forth. And so this is the Kronecker product. So you have 0, A, and so forth. So A, of course, is a 4 by 4 matrix in this example, and so 0 is a 4 by 4 matrix of all zeros. So if we substitute all that in, we get this giant matrix here. So you see here there's a 4 by 4 matrix of all zeros, which is that. And then right here, this 4 by 4 matrix, this is A that we had before. And so you see that we now have a 16 by 16 matrix, so there's 16 vertices, and from this you can see where all the edges are. So for example, vertex 1, it's not connected to itself, or 2, or 3, or 4, or 5, but it is connected to 6, 7, and 8. So 1 is connected over here to 6, 7, and 8, and so forth. So you can go through and see how everything's connected and draw this graph. So this is a second order Kronecker graph, but you could look at higher order graphs as well, third order, fourth order, fifth order. And in general, the jth order Kronecker graph will have m to the j vertices. So third order for this example would be 4 cubed. And we'll call that number of vertices n. So n is the number of vertices once you finish taking your Kronecker powers. And these Kronecker graphs are used a lot in network science to generate complex networks, and they use various tricks to do that, to generate graphs with real-world properties. Okay, so we're going to look at how to search these graphs using a quantum computer using a continuous time quantum walk. So this is a standard algorithm where you have a particle that's jumping around from vertex to vertex, and since it's a quantum particle, it can exist in a superposition over these vertices. So let's label these vertices 1 through n, and we're going to start off our algorithm so that we start in a uniform distribution over all the vertices. So the initial probability over these 16 vertices in this picture would be 1 over 16, 1 over 16, 1 over 16, 1 over 16, and so forth. So we have an equal distribution over all of these vertices. And then we evolve by Schrodinger's equation, because it's just quantum mechanics on a graph, with some Hamiltonian, where you have some parameter here that sets the jumping rate, and then this A matrix that you get by taking Kronecker power. So the adjacency matrix, this, if you do the math, corresponds to the kinetic energy of the particle. So this is just the kinetic energy term for quantum mechanics on a graph. And this affects your quantum walk, because if a particle has kinetic energy, that means it has energy of motion, so it's moving around and jumping around on this graph. And then we have a potential term as well to make it a search problem, which acts as a Hamiltonian oracle. And what it's doing is it's marking one of these particular vertices that we're just calling W, and we don't know what W is. So this term here is maybe marking vertex 7, we don't know that, and our goal is to find that vertex. And so that's what we mean by the search problem. We start with a uniform guess we evolve by Schrodinger's equation, and at some time we hope to have built up enough probability at the vertex that we want to find that when we measure the position of the particle, we find that it's at that vertex. Okay, so this is a very standard algorithm that's applied to a bunch of graphs, and we're looking specifically in this work at Kronecker graphs. So there's two main results that we were able to prove analytically, and you can look in our papers for those proofs, but I'm just going to explain what the results are. So the first result is if you have a family of graphs that has a dominant principal eigenvalue. So let me give you an example. So there's a family of graphs known in graph theory very well called the Paevey Graphs. And these are examples of Paevey graphs. You don't have to know what this math definition is, but basically here's a Paevey graph of 5 vertices, a Paevey graph of 9 vertices, Paevey graph of 13 vertices, and then there's bigger and bigger Paevey graphs. So you can keep looking at bigger and bigger initiators. And what we're going to do is we're going to look at search on this family for some fixed Kronecker power. So for example, you can look at search on the third Kronecker power of this, search on the third Kronecker power of this, search on the third Kronecker power of this, and on all the bigger Paevey graphs. And we want to know how quickly a quantum computer can search on these Paevey graphs as they get bigger and bigger. So the Paevey graphs have some spectrum that's known. So if you take the A matrix for each of these, you can find the eigenvalues of that matrix. And what you find is that it has a single principal eigenvalue that's unique and that dominates. So you see that this is order m, and the other eigenvalues are order square root of m. So this one dominates, and it's also unique. So this eigenvalue only appears once, whereas these eigenvalues can appear multiple times. So what we proved is that if you have something like this, where you have a principal eigenvalue that is unique and that dominates the other eigenvalues for large M, then search on any Kronecker power is fast or optimal for a quantum computer, meaning that it searches in order square root of n time as m gets large. And so to illustrate this, here's a plot of the success probability versus time for search on the third order Kronecker graph that's initiated by this. So the success probability starts pretty low, and then it gets bigger and bigger, and then you would want to measure the position of the particle here, and with probability of half you find that it's at the marked vertex that we're looking for. As we go up in size of the initiator, if we search on the third order Kronecker power of this, we see that the success probability is much higher now. It's close to 1 instead of about a half here. As we get bigger in the initiator, then if we do search on the third order Kronecker power of that, the success probability is now very close to 1, and it gets closer and closer to 1 as you up your Paevey graph. And so this time at which the success probability is basically 1, this time here is pi root n over 2. So we search in order square root of n time, which is the fastest that a quantum computer can possibly search. So we get optimal search in this case. So again, for any family of graphs, if it has a unique principal eigenvalue that dominates the other ones, then as you go up in the size of your graphs in this family, then you're guaranteed to search optimally. And if you want to see the proof, you can check out our papers. Okay, the next result is kind of the opposite of this. So here we upped our the graph that we started with, and we searched on some fixed Kronecker power, like the third order Kronecker power. Here we're looking at the opposite thing, where we fix our initiator, but we up our Kronecker power. So for example, let's say our initiator is this 5 cycle, which happens to also be the Paevey graph of 5 vertices. And we're going to leave this alone as our initiator, and we're going to search on higher and higher Kronecker orders. So we're going to search on the second order Kronecker graph generated by this. So this is just the 5 cycle Kronecker with itself, and you get this graph. Then it gets search on the third orders and fourth order and all the way through 8th order and as big as you want. And so we plotted that here. So here this is the first order, so search on this 5 cycle. And the success probability goes up and back down, and it's not very, smooth. I mean, it's smooth, but you know what I mean. It's not nice like this. Second order, which is this graph here, if you do search on it, the success probability goes up and back down, and it oscillates. Third order, It does this, fourth order, fifth, and you can see here now it's really starting to smooth out and look a lot nicer, seventh and eighth order. And what we proved analytically is we proved that the runtime, which is corresponds to these dots here, so that it reaches a success probability of 1 at time, again, pi times the square root of n over 2, which is optimal. So this number here, pi root n over 2, this corresponds to this red circle there. And then it's not shown here, but this blue square, this is our analytical expression for the runtime that's in our paper. And then we see that for large orders that those converge. So the expression that we have for the runtime converges to pi root n over 2. And again, this is in our paper. And so basically what we showed is that continuous time quantum walks can optimally or quickly search a large variety of Kronecker graphs. In this case, as long as the initiator has a dominant principal eigenvalue that is unique, then as you go up in your family, then search on any order Kronecker power is optimal. Whereas here, if you fix your initiator, as long as it's regular and fixed, then as you up your Kronecker order, then search is also optimal or fast. And again, more information about this is available in our papers. Thank you.